How does heat capacity affect cooling system design? Imagine trying to cool down a hot cup of coffee. The amount of heat it can hold before cooling depends on its heat capacity. This simple idea plays a big role in designing cooling systems for machines, buildings, and industrial processes. Heat capacity is a property that tells us how much heat a material or fluid can absorb or releases for each degree of temperature change. When engineers design cooling systems, they need to understand this property to make sure everything stays within safe and efficient temperature limits. The first thing heat capacity influences is how much energy must be removed to lower the temperature. If a material or fluid has a high heat capacity, it can store more thermal energy for each degree of temperature increase. That means the system has to work harder or longer to remove that heat. This is important for calculating the cooling load, which is the total amount of heat the system needs to get rid of to keep things cool. Knowing this helps engineers size the right equipment, like heat exchangers, chillers, and pumps. Component sizing is another key aspect affected by heat capacity. For example, a coolant with a high heat capacity can transfer more heat with less flow. This means smaller pumps and less surface area for heat exchangers are needed. Using fluids like water or water glycol mixtures with high heat capacities can reduce the size and cost of the system while still doing a good job cooling. It also means the system can operate more efficiently because it doesn't need to work as hard to move the heat away. Thermal stability and how quickly a system responds to temperature changes are also impacted. Fluids with high heat capacity tend to have more thermal inertia, so they change temperature more slowly. This can be good because it smooths out temperature swings, making the system more stable. But it also means the system might take longer to reach the desired temperature, so control systems need to be designed carefully to handle these delays. Material choice is another factor. When designing cooling components like cold plates or cooling coils, materials with high heat capacity and good thermal conductivity help transfer heat more effectively. This improves the overall performance of the cooling system. Better heat transfer means less energy is wasted, and the system can keep equipment at safe operating temperatures more reliably. Energy efficiency is also tied to heat capacity. Optimizing the heat capacity of the cooling medium and system parts can lower energy use. Pumps and compressors won't need to work as hard, saving power and reducing operating costs. This is especially important in large industrial settings where energy consumption can be significant. Finally, cooling systems often face changing loads due to varying equipment use or environmental conditions. Systems with high heat capacity can absorb these transient heat loads better, maintaining stable operation. This flexibility is vital in environments where heat loads fluctuate frequently, like data centers or manufacturing plants. In short, heat capacity is a fundamental property that shapes how cooling systems are designed. It affects how much heat can be stored and transferred, influences component sizes, and determines how stable and efficient the system can be. By understanding and applying heat capacity principles, engineers can create cooling solutions that are reliable, cost-effective, and energy efficient.